Welcome to The Explainer. Today, we are diving deep into a really fundamental question in computing, a kind of invisible wall that even our most powerful machines run into. We're going to unpack the true nature of speed. So, let's kick things off with a puzzle you probably run into yourself. You get a new computer, maybe it has double the processor cores of your old one, but it doesn't feel twice as fast. A 10-core chip almost never gives you a 10 times speed boost. So what's the deal? Where is all that extra power going? To get to the bottom of this, we're going to take a little journey. We'll start with how we even measure this stuff, and then we'll get into the big leagues, two legendary laws of computing that give us two very different answers to our question. All right, first things first, measuring parallelism. Before we can talk about speed, we need a way to actually see what a program is doing. How is it spreading the work out across all those processors? Okay, so the first tool in our kit is this concept called the degree of parallelism, or DOP for short. You can think of it like taking a snapshot of your CPU at any given millisecond and just counting how many cores are actually busy working. And that number, it's almost never the same from one moment to the next. And check this out. This chart, called a parallelism profile, shows you exactly what that fluctuation looks like over time. See those high peaks? That's when your computer is really firing on all cylinders, using a ton of processors at once. But the valleys? Those are the moments where things get quiet, and maybe only one or two cores are doing all the heavy lifting. Now, this graph isn't just a pretty picture. It's actually a calculator. If you were to shade in the entire area under this jagged line, that total area would literally represent the total amount of work the program had to do to finish its job. Now, I know formulas can look a little intimidating, but stick with me. This one is really useful. It lets us calculate what's called the average parallelism. All it's doing is taking that total work, the area under the curve we just saw, and dividing it by the total time it took. What you get is one single really powerful number A that tells you, on average, how many processors your program managed to keep busy. Okay, section 2, gauging mean performance. So, we can calculate an average, but, and this is a big but, it turns out how you average performance is incredibly important. If you do it the wrong way, you can get a number that's just, well, completely misleading. You've basically got two main ways to do this. There's the arithmetic mean, the one we all learned in grade school where you just add everything up and divide. And then there's something called the harmonic mean. Think of it like this. If you drive to a city at 30 miles an hour and drive back at 90, your average speed isn't 60. It's actually less. The harmonic mean is what gives you the real average for rates and speeds, the one that reflects the total time you spent on your trip. So, here's the bottom line. When we're talking about the average performance of a computer that's juggling all sorts of different tasks at different speeds, the harmonic mean is the one that tells the true story. It's the one that's actually connected to how long you have to sit there and wait for the computer to finish. All right, now that we know how to measure things properly, let's talk about the real prize. The whole reason we do any of this, speed up. This is why we build these massively parallel machines in the first place. I mean, we throw more and more processors at a problem because we want it to run faster, right? But the question is, how much faster? That how much is the speed up, and we need to define it really carefully. This brings us to a really cool, kind of theoretical idea called asymptotic speedup. It's a thought experiment. Imagine you had an infinite number of processors. What's the absolute best, the fastest your program could possibly run? This formula here calculates that theoretical speed limit for your specific program. And it's actually a beautifully simple ratio. You just take the time it takes to run on a single, lonely processor, which we call T of 1, and you divide it by the best possible time you could ever hope for with infinite processors, T of infinity. The result is S infinity, your program's ultimate performance ceiling. And that idea of a ceiling leads us right to one of the heavyweights of computer science theory, Amdahl's law. It's famous and maybe a little pessimistic, and it explains why that performance ceiling is often way, way lower than we'd like. Amdahl's law is built on one single, absolutely crucial assumption. The job you're doing is a fixed size. The total amount of work, represented here by W, does not change. No matter how many processors you throw at it, you're just trying to do the exact same job, only faster. And here is the law itself. Now let's break this down real quick. S is the speed up we're hoping for. N is how many processors we have to play with, but the real character in this story, the one you've got to watch out for, is that little Greek letter at the end, alpha. So what is alpha? Alpha is the part of your program that is stubbornly, hopelessly sequential. It's the part that has to run on a single core, no matter what. Think of it like building a skyscraper. You can have hundreds of workers building all the floors at once, but everybody has to stand around and wait while one single crew pours the foundation. That foundation, that's your alpha. That's your bottleneck. And this graph, wow, this just lays out the brutal, honest truth of Amdahl's law. See that top line where alpha is 0? That's perfect speed up. But look what happens if just 10% of your program is sequential. That's the line for alpha equals 0.1. Even if you have more than 1,000 processors, you can't get more than a 10x speed up. That sequential bottleneck just becomes a hard brick wall. So for a long time, Amdahl's law was kind of depressing for people who wanted to build these huge supercomputers. But then, decades later, a much more optimistic idea came along that changed the game: Gustafson's law. Gustafson's genius was that he just completely flipped Amdahl's main assumption on its head. He said, wait a minute, when we get a more powerful computer, we don't just run our old, small problems faster. No, we use that new power to tackle bigger, harder, more interesting problems. We scale the workload to fit the machine. And this just reframes the entire question. It's not, how much faster can I do my job? It's, okay, I've got an hour. What's the biggest, most complex job I can possibly get done in that hour? The focus shifts from shrinking the time to growing the problem. So what we have here aren't just two different equations, they're really two totally different philosophies about what computing power is even for. And this comparison just makes it so clear. On the left, you've got Amdahl's world. The workload is fixed, locked in. Time is what you're trying to change. On the right is Gustafson's world, where time is the fixed thing and the workload grows to fill it. It's really a clash between optimization and ambition. This table just nails the difference, doesn't it? Amdahl is focused on that fixed workload, and his biggest constraint is time. His law shines a spotlight on that pesky sequential bottleneck. Gustafson is all about the scaled workload. His constraint is just how many processors he has, and his law shows us the massive potential of all that parallel work. And that leaves us with this final, big question. As we move forward, what's really going to define our limits? Is it just about the hardware specs on a chip, or is it about our own mindset? Are we focused on fixing the problems we already have, or are we scaling our ambition to tackle the biggest challenges we can imagine? The answer to that might just be the true limit of speed.